All right, physics reaction video number 76. This time I did a search for one of my favorite topics, the Lagrangian, and I found this example of a bead on a rotating parabolic wire. So parabolic wire is going to make it easy to do some math. So I think this should be a cool example. Let's see how it goes.
Hello again, physics friends. I'm going to work through a specific example from the textbook in which we can practice writing and using the Lagrangian, and also thinking about stability and positions of equilibrium in that system. Okay, so the problem is as follows. We have a wire that's shaped into a parabola, and we're given the equation of that parabola. That wire is being spun about the z-axis, so the wire itself will sweep out a surface that's like a parabola of revolution. And on that wire, we have a bead of mass m that can slide freely without friction on that wire.
So what's interesting, of course, is that immediately we know that one equilibrium position is down here, right? The bead should be able to just sit there forever, experiencing no forces and happy. But it's not stable, and so if it moves away at all, it's not going to stay there. And I think everyone who might think about this problem might realize, oh yeah, I suppose it'll slide up, but how far would it go? And then there's this problem that it's a paraboloid, right? So it's a parabola-shaped bowl that we're talking about here. I guess it forms a bowl eventually. And that might be beyond people's experience, but I think that I would guess that most students would realize, okay, this is going to shimmy up here a little bit. It's funny that the image just kind of shows it sitting right there, rather than just assuming that it starts down here. But if you do some like numeric simulations, if you literally started exactly right there, it'll just stay there. So whenever I do simulations of things like that, I would just move it a tiny little bit over. And then whoop, it'll go up to some equilibrium point, which will have some, I'm sure it'll have k in there and omega in that expression. Because if k or omega were to change, I would have guessed that the equilibrium point would go to a new spot. So let's see how it goes.
Okay. And we are asked to write down the Lagrangian in terms of rho as the generalized coordinate. So this problem as framed is telling us there's only one degree of freedom, and that it's asking us to use as our generalized coordinate. It's saying, please use for your generalized coordinate the cylindrical coordinate rho.
Yeah, that makes sense.
I want to start by first making sure we're clear on why there's only one generalized coordinate necessary. Why is there only one?
So I'm going to take a stab at my explanation. I'm curious to see how similar it is to his. So one way that I talk about with my students about how many generalized coordinates are there is how much do you need to know to be able to tell where the particle is, right? So if rho is the only degree of freedom we need, like if I know that it's here, do I know where the particle actually is? Well, it's got to be above there, but hang on, it's rotating around. But I guess I know omega, so I guess I can predict exactly where this wire is going to be sort of in this as it goes around. Assuming, of course, that I guess we have to decide that at time equals 0, that it's maybe in this plane, this rho z plane here. It's interesting that it's called rho, because rho is sort of giving it away. If this had been called the x coordinate, we would have been maybe felt a little bit weird about it. So I guess it's like, how much do you need to know to be able to describe where the particle is? I guess I'll go with that. Let's see what he has to say.
1 degree of freedom. Okay, so we have one particle, which in general means that we would have 3-dimensional motion, but we must therefore have 2 constraints.
Okay.
Such that we end up with 1 degree of freedom. What are those 2 constraints? Well, number one, we're told that the particle moves on a parabola, so z and rho are not independent of each other. They're related through that equation of the parabola. So that gets rid of 1 degree of freedom. The other piece of information is, if you think about cylindrical polar coordinates, there's 3 coordinates, rho, phi, and z. So now we see that z is not independent of rho, but also we are not free to choose our angle phi. Phi is fixed such that phi dot is this constant omega.
Yeah, that's cool.
Which tells us
it's a mathematical way of doing what I was doing.
Phi right? is growing linearly in time, starting from some
Nice.
reference position,
Being
and we
explicit
can
about that,
take
that's super cool.
phi naught to be 0 without loss of generality.
this
We
right
just
here,
kind of
what
rotate
he's
the
doing
picture
right
to
here, what I was
where we
saying
want it to
before.
be to begin, and then rotate
Cool.
it there. So the key idea here is that this angle phi in cylindrical polar coordinates is not a free parameter. The particle is forced to move such that phi dot is this constant omega, which is a given in the problem. So we started with, in general 3D motion, for one particle, we've applied 2 constraints. We end up with 1 degree of freedom, and we are asked to use rho, the cylindrical coordinate rho, for that generalized coordinate. Okay. So the general approach
Cool.
I'm going to take here is,
So a little time jump there, right? Which he's using intermixed, right? So this was all written in real time, and then this boom just went in there. And so it's not clear if this is a post jump fix or if he literally hit pause, right? And so I'd love to hear from you guys in the comments the difference between those two. So the one is just keep on talking, do your whole thing, then go back and watch it and realize, oh, I bet you I could cut that part out. The other is to hit pause. Do some stuff, and then say, okay, I better unpause now. I think if I ever do it, it's the second one, because frankly, I never go back and futz with my videos after I'm done. But I can see affordances. I can see reasons why you would do both of those. So very interesting.
is the kind of foolproof approach. Write kinetic and potential energy in Cartesian coordinates, x, y, and z, and separately write those Cartesian coordinates in terms of the quantities of interest, in this case rho, and in general you can also involve t for time.
Cool.
When you make that substitution, you therefore will have kinetic and potential energy in terms of the generalized coordinate rho and time. Okay, so let's see how this is going to play out. Okay, so if we first want to write t and u in terms of x, y, and z, we want to be able to express the position in terms of x, y, and z, and
cool.
x, y, and z in terms of rho and t. So let's just refresh ourselves how to write Cartesian coordinates in terms of cylindrical polar coordinates. So I've annotated this diagram by drawing in the Cartesian axes. Z is already there. And I've kind of drawn it in a perspective where hopefully you can see the parabola here has a component kind of.
It's tough the way he's done the perspective, right? Because you could certainly imagine that the parabola looks like that and swings up at this funky angle. But this line here is would actually be this line here. So this line is getting him into trouble as far as he's trying to redraw this. But I think that by really forcing the three-dimensionality of this in the diagram, it's going to help the students. So that's pretty cool.
Lies above the xy plane, but the projection of the parabola down into that plane is given by this dotted line. And so there's an angle phi associated with the position of the bead as drawn. It's right there. And so given that, we now see that we'll call this steps A, B, and C. Step A is just to say that t is m over 2 x dot squared plus y dot squared plus z dot squared, and u is mg times the height, and the height is simply z.
Love that.
Okay? So now we're on to step B, writing x, y, and z.
Really like
in
step
terms of
A
rho and t.
and then
That's
step
where
B.
these
I love doing it this way.
parameters are going to come in. So step B, we say,
one of the reasons I really love doing it this way is if you do it this way, it's really tailor-made to jump into a computer that's always going to do its graphics in terms of x, y, and z. So we could actually easily make a simulation of this. If you follow these steps, his A, B, and C steps, I think could be really cool.
x is rho cosine phi, y is rho sine of phi, and z is given by the equation of the parabola, which is k rho squared. Okay, so now our goal is to get rid of x, y, z, x dot, y dot, z dot in kinetic and potential energy and replace it with these terms. So what that means is we're going to have to find time derivatives of x, y, and z, square them, and combine them. So let's find the time derivative. X dot is going to involve a product rule. X dot is going to involve a rho dot and then a derivative of the cosine. So we're going to have a rho dot times cosine phi.
So this is an interesting case for a jump, right? So It really is just the product rule, but I think the reason there's not a jump is because to really realize that phi is going to have some dots, and to realize that you got phi dot way down here is going to be really important. So I'm curious to see if after he does x dot, if he jumps, if he does a jump to get all of the rest of it.
Minus rho phi dot sine of phi.
Hey, cosine, do you mind if I take your derivative? Yeah, that's fine. Yeah, that's fine. What am I going to turn it into? Oh, you're going to turn it into sine. Oh, well, then stick a negative sign in front of it then. Sorry. Cosine's a big fat lazy bastard. Okay.
Right, so derivative of cosine phi is sine phi. Chain rule that.
Hey, sine, you mind if I take your derivative? Yeah, that's fine. You're going to turn it into cosine. Is that okay? Yeah, whatever. Just do it, man. You don't have to stick a negative sign in front of me. I don't mind.
That derivative of phi with respect to time is phi dot. Same thing's going to basically look, things are going to look pretty much the same for the y coordinate. We're going to have a rho dot sine, this time plus rho phi dot cosine. And we have that z dot is given by 2k rho times rho dot. Okay, so in order to find the kinetic energy in terms of our generalized coordinate of interest, we need to find v squared, right? Which is the x dot squared plus y dot squared plus z dot squared, okay? I'll write it down here. So x dot squared, I'm going to get three terms. Rho dot squared cos squared.
Again, a potential case for a jump,
the second term.
But it kind of depends where your students are at, right? I mean, the fact that it's going to be
two
first
times
out or
the
inner
class
last,
term.
right? The fact that there's a 2 there, and it's good to sort of do this slow.
Like so. That's the x dot squared. We add to that y dot squared. And we get the same cross term
because of that plus
except
there.
with a plus sign
ugly one is going to go
instead
away.
of a minus sign. So that's good. We're going to get a nice cancellation there. And I'm just
I really like how he set this up so that vertically you can
these,
see how everything is going to
my
sort of
x dot squared
simplify.
is this first row.
Oh, that's cool.
My y dot squared is the second
really
row.
Cool.
And then my
highlighting
z
instead
dot
of circling or
squared
drawing arrows
will
with
be
color. That's really cool.
K squared, rho dot squared. Okay, these first terms, I get a cosine squared plus sine squared with this.
Did you see that? The 4k squared, rho dot squared term was moving while he was underlying. Watch that. Let's go backwards. No, I'm doing the volume. Hang on.
Same prefactor.
Watch that term as it enters and then it moves. Watch.
Will be 4k squared, rho dot squared. Okay, these first terms, I get a cosine squared plus sine squared.
I have a suspicion. Let's watch it again.
Okay, these first terms.
These two things are happening at once.
cos
This is a post-video fix. See how the line is skinnier and there's not quite enough space for it? I think this was added later. Could that possibly be? Man, that's cool if it is. So let's listen carefully to his talking to see if it seems like he realized that mistake later. Ah, this is really cool. Again, hey, mistakes happen. Come on. It's all about how graceful we can handle them. And this is a super cool, graceful way to do it, right? Just say, oh my gosh, I could just go back and add it to the video later. Because I'm pretty sure that's what just happened. That's really cool.
Cosine squared plus sine squared with the same prefactor. So I just get the prefactor. The same thing is going to be true with these two terms. I get a sine squared plus a cosine squared with the same prefactor. So I just get the prefactor. And then these two final terms are going to cancel because they're equal and opposite. And then I have my z dot squared term, which is 4k squared, rho dot squared. So now I have a kinetic and a
I think it happened again. Because the line thickness changes. Let's see if we can hear a little click sound before that gets written. Let's go back. Try a little bit more. Okay, let's go.
So are going to cancel because they're equal and opposite. And then I have my z dot squared term, which is 4k squared rho
I'm not sure I
squared
heard it.
rho dot squared.
Really interesting.
So now I have a kinetic and a potential energy, which means I have Lagrangian. And my Lagrangian
All right, because the
will
potential is
involve
already in terms of
rho,
z, which is super easy
rho
to write
dot
down.
and time.
Cool.
Okay, and why do I see that it's going to involve time? Well, remember, phi dot is not an unknown function. Phi dot is omega, the rate that the parabola is spinning.
Cool.
And we are told that that rate is constant. So I'm going to come back to this equation, and I'm going to write it only in terms of rho and the constant omega as well as rho dot. There is some. So we have here rho dot squared plus omega squared rho squared plus 4k squared rho dot squared.
Cool. Now everything's skinny.
That's
I'm not sure
our
what
v
happened there.
And so when all is said and done, we finally end up with an expression for the Lagrangian. As
Nice.
shown here, it's
Nice
m
little
over
jump.
2v squared minus mg times the height z.
Cool.
So I've moved things around just to buy
Oh,
us some
nice.
space here.
Shrunk.
We have our Lagrangian.
Nice.
And now we're trying to find the equation of motion for the bead and study the motion of the
There's
system.
definitely only one
So
term in there. There's just rows
There's
in there.
one
Very cool.
Lagrangian here, but there's also only one Euler-Lagrange equation because there's only one generalized coordinate.
Mhm.
That coordinate is rho. Okay, so we're going to need to compute partials of the Lagrangian with respect to rho and rho dot. Let's start with rho. We march through, there's 1, 2, 3, 4 terms. Rho doesn't appear in the first one, so that goes away. This term gives us 2.
You know, it's funny, that phrase he just used, rho doesn't appear in the first one, right? This is always a struggle because the students are like, well, I wrote a row. Yeah, but it's got a dot over it, right? So when we're doing these partials, we really only want the naked rows, the ones without dots over them, right? So it's really interesting to realize that students can skip this term. They're not going to be able to skip this term. So that'll be interesting, right? So you got both of them sitting right in here, but only this one's going to affect the derivative. So this is tricky.
Omega squared rho m over 2. So that's just omega squared rho times m. Like so. Second term, we're going to get an 8k squared rho dot
Squared.
times m over 2. So that's 4 mk squared rho dot squared. And the final term will get minus 2 mgk rho. We similarly look at the partial with respect to rho dot, and we get the following: m rho dot plus 4 mk squared rho dot, and that's it. The final piece is that we have to take the time derivative of that second partial, and we get m rho double dot.
Nice.
But
Nice
then we
and
have a
easy.
product rule on the second term, plus 8 mk squared.
And this second term
rho
here is really the
times rho dot, and we get two factors of rho dot, one from before and one from the time
centrifugal
derivative.
force, right?
And then we also have the derivative of the second term,
Oh, it's also the
which is the rho
Coriolis
dot
force.
term. So rho dot becomes the rho double dot. Now our Euler-Lagrange equation tells us how to combine those two partials. And it says ddt
It's
of
interesting
the
that these
partial
two
with
terms,
respect
this
to
term and
rho
this term
dot
don't
is
cancel.
equal to the partial of L
It'd be
with
nice if they
respect
did.
to rho. Okay, so we see a couple things. First of all, every single term has an m in it, so we're just going to drop the m because it cancels
Nice.
on the left and the right side.
Nice.
And then we can also do some grouping.
So as soon as the M cancels, you'll get the same result no matter how massive the bead is. That's super fascinating because you might think, you spin the sucker around, you're like, oh, this bead goes to about here. And then you might ask the students, okay, well, let me just stop it for a second and make the bead much heavier. Where's it going to go? I would guess most students would assume it's going to come down here. But if mass truly cancels, no matter what answer you get, it's going to go to the same place. So that's actually really interesting.
So we have two terms that are rho double dot. So we're going to group those two terms on the left-hand side. Rho double dot, 1 plus.
All right, so I just took a look at the time. So I'm going to fast forward here till we get to this stability argument, because the equations of motion, find the equation of motion, that's kind of boring. It's basically this. This equals this, done, right? But I'm really interested in this equilibrium thing, because basically he's going to say, well, where if you set rho double dot and rho dot equal to 0, what is rho? And is that stable? So I'm just going to fast forward through until we get there. Okay, don't need any of that. Yeah, so then equals that. Okay, and there's our equation of motion. And then here he must be talking about the stability. So is he? Yeah, okay, so here, let's just go back and listen to him say that.
Bead can remain fixed. What that means is that rho dot and rho double dot are both 0 because rho is a constant. So we can now simplify. So if we look for rho equals constant solutions, meaning that rho dot and rho double dot are 0, that means we can simplify our expression.
This is going to be 0 here.
So
sure enough, K and
first
G
thing is this whole first term is
answer.
gone because it's rho double dot. This whole second term is gone because it involves a rho dot. So all we're left with is this, and that tells us that 0 equals minus 2gk minus omega squared rho, and that implies that we need omega to equal the square root of 2 times g times k. That gives solutions.
Whoa, wait a minute. I was assuming there would be a rho answer. There's not a rho answer. This is stable. Well, actually, we haven't checked stability. This means it's if you set omega to this value, those are equilibrium points. I guess we haven't checked stability yet. And that I did not expect. So does that mean assuming it's stable, and I mean, you'd have to do a little bit more work to prove stability, does that mean that you can set it anywhere? Whoa, that's cool. Let's see.
With constant rho. There is, of course, one other way, and that is if rho itself is 0, then that satisfies this equation too. So there's another case, which is rho is 0. What that means is that your bead is sitting down at the origin, and as the parabola spins, the bead will remain at the origin. Okay, so both of these are solutions. So we have solutions, but now we want to understand, are these stable?
All right, yeah, that's what I want to know too. I'm just going to get to it here, see what he does. Who cares about case 1? Who cares about case 1, but let's see what he's doing here. Yeah. I'm way more interested in case 2, but I'm curious what's happening here. Yeah, anything that's squared is 0. Oh, okay. So that's only stable if 2gk is greater than omega squared. So this case 1 is interesting.
Of motion that looks a lot like a mass on a spring, right? I mean, it's a function's second derivative gives you back minus a constant times that function. So this is stable as long as the term in the parentheses is positive. So this is stable if 2gk minus omega squared is positive, so that the overall relationship between epsilon double dot and epsilon has an overall minus sign.
Cool.
Okay, so we have a condition now.
Man, I'm just dying to just quick model this. I'm gonna hit pause, see if I can model this, because now I just really want to see this. I think that the way he set this up is so very cool. I really liked so many things that he did. I love his A, B, and C approach to how to do this problem in the first place. I love this constraints argument, which was different than my hey, how many things do you need to know where it is argument. I thought that the work to figure out to put all of the things in terms of rho was awesome, and got to here. And then this stability argument I really liked. I actually didn't care about the rho equals 0 case. I just thought it was going to always be unstable, but I'm wrong. Turns out it's sometimes stable. So I'm just going to hit pause and see if I can do some simulation. If it doesn't work, then it doesn't work. Actually, I think I'll just make a different video. That sounds easier. So hey, you guys, this was super cool. I love this Lagrangian stuff, and I really thought the way that he did it was super awesome. And even though I skipped through this, I'm really loving the way that he talked about linearizing this. Man, that was really cool. And there's even more in this video, so check it out. All right, everybody, have a great day. I'll make a video of the simulation if I can get that to work. And remember, physics teachers are awesome.